Okay, this is AP Environmental. This is your first video. Congratulations. We're going to start with the geology unit, and so we're going to start looking at the Earth system. So we're going to start with origin of the Earth, origin of the universe. This kind of just summarizes everything for you. So you're looking at the different pieces here. So the universe was created 15 billion years ago in the Big Bang, is the current hypothesis. Obviously we can't prove any of this, but that's what people accept at this point in time. The solar system was created about 12 billion years ago through the nebular hypothesis. And I don't really need you to go into what the nebular hypothesis is. I just want you to know that that's what people accept at this point. And then the Earth was created about 4.5 billion years ago. And we're going to talk about hypotheses for that one in just a minute. Okay, so looking at the planet over time, the past 4.5 billion years have been very, very different. It was absolutely not like what it looks like today. Hadean time is the first approximately billion years. Earth was a molten planet. It was all liquid magma. Excuse me. Hit by meteorites very frequently, very dynamic. The atmosphere was not present. There was little or no liquid water. There was some water vapor in some very remote places, but that's about it. And then the Archean era had widespread volcanism. So a lot of volcanoes, a lot more active stuff. The magma was moving around. A lot of heat energy was released. This is what formed the crust, the surface of the Earth. And the beginnings of the atmosphere was the volcanic action, because as you know, volcanoes will release not only, let me go back. Okay, volcanoes will release magma or lava after it's released, right? But they also release a lot of gases and a lot of other liquids, water vapor, stuff like that, that will turn in, or gases that will turn into liquids. So all of this right here helped to form the atmosphere and the hydrosphere, and then the magma and the lava cooled off, solidified, and formed the Earth's crust. This is when we're starting also to see complex cellular life. Very, very basic compared to what we have now, but we're starting to see stuff. Okay, so after that, the Earth became what they call differentiated. So as you see, you start out with this very, very homogeneous planet, same throughout, nothing different. But as time goes on, you see that you start to end up with these layers, and these layers are different. And you turn into a planet right now that has excuse me, multiple layers that are heterogeneous within themselves. So to help you guys a little bit, I don't like this inhomogeneous word. The better term is heterogeneous terms. So you see that all the heavy and the more dense stuff is going to stick to the center, that's the Earth core, and then you move out from there to the less dense. So about 3.5 billion years ago, things started to calm down. This is what we call the primitive Earth. We have a very basic atmosphere composed of a lot of methane and nitrogen compounds, water, gas form, water vapor, and carbon dioxide. The crust has sections in it, is divided up into different plates, but everything is in, all of the land is in one supercontinent. One supercontinent. So we don't have, this is even before Pangea. I don't know if you guys realize, but there were a whole bunch of steps before we hit to Pangea. So Gondwana land is the first supercontinent. Okay, so after about 3 billion years, and then moving towards us on the timeline, we start to see photosynthesis. So that's a huge deal. Once we hit photosynthesis, we start to get the production of oxygen, and oxygen creates, obviously, life. So the oxygen reacts with the carbon and nitrogen compounds, releases nitrogen into the atmosphere, and then the oxygen gives the atmosphere animal life capabilities. So once we hit photosynthesis, which started from a blue-green algae that is anaerobic, so it didn't require oxygen to start with, we now have oxygen, and we can now start seeing more complex life that is oxygen-based. We still have blue-green algae in a few very remote places in the world, and it's very similar to what it used to be actually at that point in time. So looking at the Earth as it is now, which is pretty recent relatively, less than 1 billion years, we see a blue marble is the term for it. So we divide the Earth into spheres according to the characteristics and the type of materials of each sphere. We have to, this is really important right here, we have to consider the Earth one big system with a finite set of resources. Nothing is infinite. There is a specific limit that we will reach given enough time. So these are the 4 different spheres of the Earth. This is what we divide the Earth up into: the lithosphere, the atmosphere, the hydrosphere, and the biosphere. The lithosphere is a solid part of the Earth. That's the rock and the soil, sediment, all that kind of stuff. This is the plate, so we're going to talk about plate tectonics in a few minutes. And it's a source of most of our resources. Obviously, all of our mining, all of our elements are coming from the lithosphere. The atmosphere is the gases that envelop the Earth, extend out away from the Earth's surface. Nitrogen from the primitive atmosphere, water from volcanoes, and oxygen from oceanic phytoplankton. And this is kind of interesting. It's actually phytoplankton that provide most of our oxygen from photosynthesis, not the rainforest, trees, and stuff like that people think it is. We depend much more heavily on phytoplankton than we do on rainforests. Not that rainforests are not important, but in this case. Excuse me. Okay, so the hydrosphere is the water that covers 71%, about 70% of the surface of the Earth. Ocean, lakes, rivers, streams, and then groundwater. So people often forget to include the groundwater. That's all the water that's from rainfall, that's soaked into the Earth's crust. This is underground water or surface water. They both kind of lump into the same category of groundwater, and is actually a significant amount, and we have to take that water into account when we're looking at the whole water cycle overall. The biosphere is the organic realm. This is all the life: plants, animals, protists, fungi, so on and so forth, bacteria. So this is something that we're going to come back to a little bit later. I want to focus on the geology for right now. Okay, so the solid Earth, 3 layers: core, mantle, and the lithosphere. The core of the Earth, the very center of the Earth, is metallic. The inner core is solid. The outer core is molten. And the internal source of heat energy. It is the internal source of heat energy for the Earth. So this is where our energy is coming from, is this right here, because it's so hot. All of the energy is in the form of heat. The mantle is the next layer. The mantle is the middle section. It's very rocky, but it's also molten for the most part. It has kind of like chunks in it. And it has convection currents. So those currents are what drive the plates in the lithosphere. So you see these, hang on, sorry, let me go back, my arrow disappeared. So you see these currents that are moving right here, that's moving the plates over the surface, and this gets into the plate tectonics theory that we'll talk about in a minute. So the lithosphere is the plates. This is the rocky boundary, solid for the most part, and even over the ocean, there's ocean floor, and that's what we're talking about when we talk about the lithosphere, is those plates. So we see the oceanic crust and the continental crust. So whether there's water on top of it or not doesn't matter. It's all considered the lithosphere. This plastic asthenosphere, that's where there's a lot of stuff moving around, the currents and stuff moving around. Okay, so plate tectonics, and the plate tectonic theory is that the Earth is divided up into plates. We have significant evidence that this is actually happening. So you can see these boundary lines, and we'll look at some of these. We have some activities to do for these, so we're going to look at this a little more closely. But what you see is you see all these plate boundaries, and you see the Earth divided up into these plate boundaries, and all of these plates are in fact moving. So we are on the North Atlantic plate that stops in the middle of the Atlantic Ocean, and then along the coast of the Pacific. Pacific U.S., and that plate is actually moving in that direction. Our plate is. The Pacific plate is moving in that direction. So we actually see that the Pacific Ocean, in time, will be getting smaller over thousands of years, and the Atlantic Ocean will be getting bigger over thousands of years. And we're talking, on the order of maybe a half of a centimeter per year, if not less than that. So, nothing significant, nothing that we would notice even in our lifetime. So the theory of plate tectonics is that the plate movement, the movement of the lithosphere over the asthenosphere and the Earth, gives us volcanoes, earthquakes, mountains, rift zones, or any combination of these. So essentially, all the geologic activity that we talk about is caused by plate movement. That is a summary of the plate tectonics theory. Okay, so this is where things get really crazy. These are all the options, and we're going to do some activities on this, so I'm just going to let you guys kind of look through this. Make sure you pause here and kind of look at the difference between a convergent and a divergent plate boundary and a transform plate boundary. What's happening in each place. Have an example of where in the world one of those is. So like if they ask you where's a convergent plate boundary, where would that be? And we're going to look at this in much more depth. So make sure that you know the difference between those three. They're pretty self-explanatory. And ask me if you have any questions. So the heat energy from the core of the Earth, remember I said that was really important. That's where we get all of our energy. Is transferred into mechanical energy in the asthenosphere, so in the mantle. Okay, so what happens is you have this heat in the core. It radiates from the core to the asthenosphere, which is the mantle. And then that drives the plates. The mantle has those convection currents. And the convection currents push the plates of the lithosphere around into new shapes and sizes. That's why we had, we went from that one supercontinent to Pangaea to all the others to Earth, or to what we have now, to the 7 continents. And that's why we have all of the geologic activity that we have today. Okay, so in addition to that, the pressure and the heat energy, or the heat energy causes high pressures. Pressures that are high enough to change the structure of a rock, the crystal structure of a rock, is a metamorphic process, and that results in a metamorphic rock. A temperature high enough to melt the rock and therefore reshape the crystalline structure result in magma and igneous processes, and that would be an igneous rock. So we can actually look at the type of rock and know how and where approximately it was formed, and we can date that as well. The water cycle and gravity provide the mechanisms to break everything down. So whereas before we were building rock with heat and pressure, now we are breaking that rock down into sediment. That water cycle and gravity result in weathering and erosion. I think a lot of this will probably be a review for you guys. Weathering is the breakdown, like acid rain or just rain itself. Will hit and cause pitting in rocks, cause breakage in rocks, and that breaks down eventually to sediment. And the same for erosion. So the Colorado River through the Grand Canyon, this used to all be flat, right? And now the river has worn away, so it gets deeper and deeper and deeper. Rock cycle, make sure that you are comfortable with the rock cycle, please, that you know the different parts. There's only really three different types of rock: igneous rock, sedimentary rock, metamorphic rock. And again, we'll look at this in more detail in class. And so they can go between the three of them. The temperature and pressure changes. So extreme temperature and pressure changes sedimentary into metamorphic. Extreme temperatures melt into igneous. And then weathering and erosion go back to the sedimentary. Deposition and lithification is like becoming a solid, essentially. So you deposit the sediment, and then that sediment cools off, dries, hardens, and becomes a solid sedimentary rock. So those are your processes, but you can go between really any three. You can have a metamorphic rock that undergoes erosion, turns back into a sedimentary. You can have an igneous or a metamorphic that undergoes a pressure change and turns into another metamorphic. So there's not really any set rule there. Continuous cycle happening all the time. Okay, so the atmosphere. So we've done the lithosphere. Now we're moving to the atmosphere. We're going to do a lot more of the atmosphere when we talk about air pollution and climate change. But for now, what I want you to be comfortable with is that it has several layers. There's different temperatures, different pressures, and different compositions. And you can take a look at this. Like I said, we'll get into this a whole lot more in more detail later on. Hydrosphere, same concept. We'll get into this in more detail later on. This is the water part of it. You can see very clearly a few things looking at this graph. You can see first off that the coral and the mangroves are, prefer warmer water, clearly. You see that lakes actually prefer more temperate climates. You see the major lakes in more temperate climates. And then you also see that rivers always lead to ocean somehow, right? Or a lake, in whichever the case may be. Okay, so water's properties. Again, this is just super quick review. Read through this, make sure you don't have any questions. Hydrogen bonds keep high surface tension, keep the capillary action that allows water to move up trees in order to keep trees hydrated. Water has a high specific heat, doesn't change temperature quickly, so high carrying capacity, a lot of energy, so it is able to carry energy around the globe. It's the universal solvent.
Please mark this interruption. If you are parked in the student lot where the band practices, please make sure that you have moved your car by 3 p.m. because of
It will dissolve anything.
make sure that all cars are
It expands as it freezes. That causes a lot of erosion and weathering, and obviously animals need it. So just make sure that you don't have any questions on this site. Ionic compounds ionic compounds will deionize. Organic compounds don't break down based on their molecules. Ionic compounds will. Okay, so this is stuff that we're going to come back to when we talk about the ecosystems, but essentially you have a limnetic zone that's out in the middle of a lake in deep water and a littoral that's shallow where you have plant growth. So this is like a coastal thing. This, we're going to go into a whole lot more detail. This is incredibly a lot of information on one slide. Different zonation for oceans. We see a coastal, which is, the term for this is neritic, and then oceanic, and then you see euphotic, or photic is a more accurate term for oceanic stuff, and then aphotic is anything that is no light. Benthic organisms live on the ocean floor. Pelagic organisms live up in the water column. You see the difference. The continental or the coastal zone has plant life because there's light going down. Notice that the coastal zone ends when there's no more light, and then the oceanic zone is beneath that. Okay, same concept for a lake. So we see the limnetic is the aquatic, the lake version of a photic zone, and then the profundal zone is no light. So you see the difference there. The littoral, close to shore, limnetic, out to sea, or out in the middle of the lake. Biosphere, more to come later on the biosphere.